Welcome to my live stream channel. Today, as you guys have clicked on the thumbnail, today we are going to explain and understand uh, the motors, the products that were the result of AC and DC of Edison and Tesla. Sorry, Tesla and Edison. Edison was on the side of DC and Tesla was on the side of AC. So today we are going to understand the overall electrical system behind these two motors. So again, this will be a more like engineering and technical stuff to be deal around. But if you have any idea about the physics, the electronics, the electrical systems, or even you are from like the high school or something, you can still relate to it and you can maybe learn something from this. So this will be our basic syllabus. The main syllabus we are going to focus on this one. Okay, so you might think that this is a like engineering class or something, but although it is inspired from the syllabus and all, but we will see the technical differences between all the things. Okay, the chapter before that, the subject name is electrical drives. Okay, electric drives. In the first unit, we will have the introduction and the concept, the different types of the electric drives, the classification and their components with the characteristics. Okay, all of these things. In the second unit, we will have the choppers, the devices. In the third unit, we will have the different methods of speed control. Okay, uh, and all the other things. Okay, in this first unit, we'll also have the braking and speed control. So again, if you like the technical terms, this will be a very good topic to learn. And then we have PMMC, radial, axial, sinusoidal, all the type of systems. Okay. In the last unit, we have the system construction, that is of the motor drive, the reluctance motor drive, the designing, the design problems, all the other things. So this will be a main syllabus. Apart from this, let me just switch on the window drives. Yes. So this is my handmade note, so we can understand better and in a very concise manner. This will be the you know a detailed note. This is from a university. I don't know which university. I just downloaded it, and this is from another university. So some of the topics are given in detail here. Very much detail. For example, this four-quadrant operation of DC drive. How will the DC drives perform in the different quadrants? You must know by this time that there are four types of quadrant: first, second, third, fourth. So this is that the control. Okay, and in this one, we have electric braking, the dual converter, the closed loop, all the see every university or any college doesn't necessarily coincide with another college's syllabus. So we have to look for the topics. Although some of the books, like this SKP book, is everywhere. In this one, I think it is in this one also. SKP, yes, and it was in the main syllabus also. So uh, will be like a fun engineering class. It will be more on theoretical basis. There will be no like 3D models or something. All the things will be on PDF and paper. And you guys just let me know that if you want these resources, I can share. So, speaking of resources, let's start. As you have known, the first was introduction and all. So, I think this is also introduction, but it is just directly getting into the topic. Okay. What about this one? Let me just see in front of you guys only. Okay. We have fundamental concept, definition. Okay. These are the okay, advantages, introduction, the same thing, block diagram. and this is my notes. So let's start with the notes, and we will gradually move on to the textual notes, more like technical notes. So electric drives, more the students which are from like science background, electric drive, it sounds like, two different things. Like, sir, is it motors or something else? Actually, drive in the literal meaning, it is to drive something, to carry something. So in this electrical system, you can say that it carries the electrical force, okay, and delivers it a type of, in this context, it is a mechanical force. So an electric drive is a type of device which drives the electrical force, okay. Drive, motion control system, yeah. Motion control system are known as drives. It will drive a load. So uh, I was kind of wrong, but you get the concept, okay. It drives a load, and the load is obviously mechanical. So it is a machinery designed to accomplish a specific task. We have source, power moduling, motor, and then load. And this is a feedback system, sensing unit. It gets the feedback, control unit, and it changes the system settings according to that. This is the block diagram. Load is broadly classified in the terms of speed and torque. Oh, okay. So if you guys are from uh, anywhere near ninth, I think ninth or tenth. Okay, tenth grade. So if you must have known between the difference between the speed and torque. Okay, so speed is a scalar quantity and torque is the vector quantity. Okay, let's give some attention to these. Which one is? Yeah, they looks like same. They're pretty same. Introduction C, module one, electric drives, the steady state efficient, IGBT, steady state efficient. Ah, these both are the same. Okay, okay. Till some multi-quadrant operation, and here we have something in it, multi-quadratic operation. No, we don't have it. So this one is better. I think this one is better. Let me see the. Mm, okay, thermistor, DC motor control, and here we have what? Just okay, speed torque characteristic. Okay, we will focus on this one only. So, introduction to electric drives. Guys, motion control, the same thing written in my notes. Motion control is required in large number of industrial and domestic applications. So, as I have mentioned Edison and Tesla in my, you know, thumbnail, at the time of these two guys, the industrialization process was on the, a very upsteep, what do you say that, uh, very high slope graph. So industrialization was there. Yeah, it was just there. So we needed heavy equipments, heavy motors to drive the loads, basically do something on a very large scale. So systems employed for getting the required motion and their smooth control. It can be loading from a ship or anything at thing at the industrial level, no? And at the domestic level, we have ceiling fans. The best example, it is a type of AC motor. But in the market right now, you can see the advertisements and the trend of a type of ceiling fan that is controlled by the remote, and it is labeled as BLDC fans. The BLDC stands for brushless direct current fans. So in now modern times, we are switching from AC to DC fans. Okay, there is a type of circuit in there that changes the AC current to DC current, that has its own benefits. But sir, if Tesla was correct, then why we are now moving to DC? See, AC is best for transmission. The power, the energy, the electrical energy has been the electricity has been transmitted from the power line to your house. Now, it's your choice. You can use the AC current, or you can convert it to DC, like the mobile chargers, adapters, or that thing. Everything has in its benefit. We'll see when we'll study in detail. Okay. So, systems employed for getting the required motion and their smooth control are called drives. If you want, you can make notes with me. So, drives are what? Motion controlled devices. Okay. The drives require prime movers like diesel or petrol engine, gas or steam turbines. Oh, these are prime movers. Prime movers means these are the starting sources. You can't generate electricity from nothing. Okay, thin air. So that is what it's saying. It's nothing like we need. We can classify non-electric motors as drives. So that is just drives, not electric drives. Okay. So this is a drive. These can be the source of energy. These prime movers deliver the required mechanical energy. Remember, I just said deliver. So drive, deliver, same thing. So these prime movers drives the required mechanical energy, delivers the required mechanical energy for getting the motion and its controls. Drive employing electric motors as prime movers for motion control are electric drives. So basically, drives which are using electric motors, that is called electric drives. Now, the advantages of electric drives. As the electricity industry was growing, we were seeing the benefits, the advantages of electrical drives. So this is all about energy engineering and industrial aspect of motors, so drives. So now their advantages. We'll go through each one of them. The steady state and dynamic performance. You must know the state and the dynamic performance, you guys. If not, steady state is when, like, when you start a motor, the voltage strikes to what it should be, then gets back down, then it takes times to get on a constant level. And that level, when it reaches there, it is called a steady state. And dynamic performance is like when it's in motion. So a steady state and dynamic performance can be easily shaped to get the desired load. Yes, we can control the steady state when what will be the value, and the dynamic performance is the speed and torque. So can be easily shaped to get the desired load characteristics over a wide range. Wide range means you can go from few RPM to thousands of RPM. It depends. So that is the first advantage. Okay, second one is efficient starting or braking is possible with simple control gear. Yeah, if you imagine there is a mechanical drive, it will be very difficult it, to start it. You have to put the whole system in motion, or you have to just overcome its inertia. So that is all the things. But in electric drive, the starting and braking is pretty easy, and we can do this by the use of control gear. Control gear is basically power panel, the control panel. Okay. Third one is with rapid development in the field of electronics and like the semiconductors industry, we got SCRs, MOSFETs, IGBTs, these things. The transistor based electronics. So what these guys did was they helped in designing of efficient power converters to feed power to the electric drive that has simply become easy. So efficient power conductors, just in one point. So keep in mind, we are still not discussing about whether AC is good or DC Tesla is good or Edison is good. We are just starting with the basic concept. We are getting to know the drive, the machine. Then we'll go deep into that. So if you like this sector of study, please show your support. The fourth one is with the rapid development in the computers, PLC, microcontrollers. What is HW and SW? Hardware and software. See, sometimes even I don't get it. So, with the rapid development in computer hardware and software, PLCs, programming language, controllers, microcontrollers, which can easily perform the control unit functions, has become easily available. Okay. So, computer friendly. In one word, I can say it's computer friendly. Okay, try to make short notes. Don't remember and write all of these. The fifth point, electric motors have high efficiency, low losses, considerably overload capability, have longer life, lower noise. Okay, so we can just say electric motors are good, or electric motors are have aura. They are great. Okay, they can operate in all four quadrants. Very special, guys. Oh, sorry, very important, guys. They can operate in all four quadrants. The quadrants being our real, imaginary, imaginary, and real imaginary. So basically, positive x-axis, positive y-axis, minus negative x-axis, positive y-axis, negative, both x-axis, and negative y, positive x. So these are all the four quadrants of operation in the torque speed plane. So this is the Cartesian plane. The characteristics will be the axes will be torque and speed. The resulting electrical braking capability gives a smooth deceleration, and hence gives longer life for the equipment. So we can say the seventh point will be. I will break this point into two parts. One is all four quadrants, and the other one I will write to like it energy saving and longer life. Yeah, or you can also write better braking. Hmm? So I will write longer life and energy saved. They are powered from electrical energy, which can be easily transferred. Yes, this is a very great point. As I was mentioning it, electrical energy is the best type of energy to transport or transfer. Okay. Next, block diagram of an electric drive. Remember my notes? It was quite like this: source, power module, motor, and then load. We have a feedback system, sensing unit, and control unit. Let's see. Here we have power source. Power source. Yep. So first of all, it is shown in the figure below. Parts of electric drive, different parts. Okay. The first one is, let's just draw the block diagram first. Then we will study these. We have power source, power converter, then motor, and then load. And before load, there is a feedback system, which have a sensing unit and what else? Control unit. Okay. As you can see in this block diagram, there is one more extra thing, that is input command. This input command, I didn't made it because it is included in the control unit. It has a preset value and it gives into the source. And here it gives into the power converter. So basically same thing. It should not be in the source. It should be here or here. So this was in a hurry, I think. Power module, power converter, same thing. Okay. I would give this arrow to here, but okay, that doesn't matter that much. So you got the essence of an electric drive. Now let's study or get a glimpse at all of these individually. The load can be any of the systems, as we know in the industrial or residential, sorry, commercial use case. We have pumps, machines that carry out specific tasks, like submersible, cranes, all these things. Usually the load requirements are specific in terms of its speed, torque, demand. Yes, it means what this line means is some uh, devices need more speed than torque, and some need more torque than speed. An electrical motor having the torque speed characteristics compatible to that of that load to be chosen. It means, for example, this load has high speed, less torque. So, an electric motor that needs a high speed, low torque will attach to this. Okay, then it will perform the best type of system. Power converter, the main unit, performs one or more of the following functions. Okay, what it does is it converts electrical energy from the source into form of suitable motor. So what is saying is, for example, the motor you are using at the load, it can be Tesla motor or Edison motor. If you are a fan of Tesla, you are using a Tesla motor. So, or maybe Edison motor. So at the load, we can have AC or DC motor. And now think about it. If you are practical and saving your money, you will use AC power source to, transfer the energy. But you are a huge Edison fan, or it's just feasible to use DC current to transfer, you will use DC power source. So what this converter will do is it will convert AC to DC or DC to AC according to your need. Okay. For a DC motor, AC to DC, and for the induction motor, DC to AC. Okay. That's the main thing it can do. Okay. So if you have this part in your system, congrats. You can uh, put the input any of the two and get the output according to you. So AC to DC or DC to AC. Imagine this being at the time of Edison and Tesla. Both would have collapsed. Okay. Next is, but we are not sure about Edison. Controls the flow of power to the motor so as to get the torque speed characteristics acquired by the road. Okay. Now we got it. We got the type of current we need according to the motor. But now, as we have discussed, sometimes we need a high speed low torque or low high torque low speed. So it will identify. See, we don't know how it will identify right now. We'll study. So according to the load, it will change the characteristics, the torque speed characteristics, and then that type of load is treated accordingly. So two main things what? The only two main things are in this whole system is these two main things, and this guy is doing all alone. So this is the most useful unit, controlling speed, torque, characteristics. Next, during transient operations, transient is Remember, I was talking about steady state operation. The steady state time is when the motor gets constant. The voltage gets constant. For example, when you start a motor, the voltage should be around here. It will peak here, then go down, then here, like this, and then at after few microsecond, millisecond, second, it will be constant. Okay, that constant time is known as steady state, and the fluctuating time is known as transient. Very easy. Okay, got in your head. So during the transient operations such as starting, you know, even braking, speed reversal, limits the current to permission levels to avoid conditions such as voltage dips, overloads. So at this time, we have to be very careful, okay, as the voltage can dip too low or overload. All these things can happen. So the third task this module is doing is at the transient phase, limits the current accordingly. This word is very important. We don't know how much limiting do we have to do. So accordingly, selects the mode of operation. Okay, this is also selects mode. What does it mean is we have to do motoring or braking. For example, the required speed at the node was 1100 RPM, and according to the power converter, the RPM is of the system is right now 700. So it will do motoring. It will increase the speed. And after receiving like 1100, and even after crossing 1100, it will reach 1150 RPM. And then it will get the feedback and realize, oh my God, we are uh, crossing the line. Yeah. So it will do braking and then get reduce the speed to 1100 RPM. That's the example. So that is the functions. Now pipes, what I'm even saying. So types of power converter. So now we have options. Congratulations, guys. You can choose which type of power converter are you going to use. So let's see types of power converter. We have depending upon the type of motor used. So basic, one of the most basic and used one AC to DC. They convert single phase polyphase. Polyphase just means a fancy way of saying three phase. Single phase, three phase AC supply into fixed or variable DC supply. Fixed or variable means the DC can be variable, like it can change 5 volt, 8 volt, 7 volt, and fixed is just one. The variable DC is the mobile chargers, not the Apple one, the more technologically advanced ones, which have three types of output. For example, it is saying 18 watts of fast charging. Okay, so in some of the adapters, it is mentioned. You can look. You can Let me just search a picture of adapter. There are options of output. Okay, 18 watt can be achieved by multiplying 9 into 2. So 9 volt, 2 ampere. Also, sometimes it is 12 watt and 1.5 ampere. So now you can see the output is varying. Let me just show you. So this is a type of varying DC output. Okay, this one, does this one have it? Or this one? Guys, I've got this. Like, let me just show you. Which one is this? Chrome? Is this Chrome or this Chrome? Which Chrome is this? I got this. Why aren't we getting this? Come on, man. Okay, okay. Let me just download it then. Save images. Save images. Okay. Uh, adapter. Now we can just open it. Now I can just show. Where is this? Close this one. Now it must be there. Yes, it is. Oh, there is none. The screen is still blank. Okay, let me activate this one then, and then, yeah. Okay, guys, here is the screen. Now you can see this. Okay, as you can see here, that the output is fixed. That is 5 volt DC. Here, the output is fixed 5 volt DC. In some of the chargers, we have this is 5 watt only. Let's assume it's 18 watt. Then we have 9 volt, 2 ampere, 12 volt, 1.5 ampere, all these things. Okay. So moving on with the PDF. Then we have, where were we? Oh, yeah. And it can be achieved by using thyristors, IGBT, MOSFETs, depends. AC voltage controllers or AC regulators. What is this? This brings down AC to AC only, depending upon the requirement. Okay. What else we can say this? Just transformers. You must know what is a transformer. Transformers is a device which can transmit AC to AC, but changing the it can or can be. It depends on you and the number of turns. So you can step up the volt or step down. Okay, so these are those are called transformers. So AC voltage controllers are just AC regulators are just made using the transformers. It can be auto transformers with various taps, converters, all these things. So DC to DC, okay. AC to DC, AC to AC, DC to DC. So let me just wait a minute, just write it. So AC to DC converter, the first one. AC to AC, we call it regulators. Then DC to DC, converters. They are used to get variable DC voltage from a fixed voltage. Okay, now you were getting 5 volt only, now you can get 2 volt, 3 volt, 4 volt. You can get a variable amount of DC from a fixed volt source. We got inverters, yeah, the opposite of converters. So, which can do DC to AC. I think, yeah, they are required to get variable voltage, variable frequency from DC using PWM. Yep. Cycloconverters. They convert fixed voltage, fixed frequency AC into variable voltage, variable frequency AC. So what this means is this means cyclo, con, and above we have inverters. Okay. So inverters change DC to AC, and cycloconverters, what they do is, for example, you're getting fixed voltage, 240 volt, uh, 50 hertz. Now you can change into 100 volts, 30 hertz, 100 volts, 60 hertz, 40 volt, sorry, 150 volt, 60 hertz. It depends on you. You can use cycloconverter for that. So we have fixed AC to AC. Next, we have the control unit or the sensing unit. Both work together. The control unit controls the operation of the power converter based on the input command of the feedback signal continuously obtained from a suitable point in the closed loop. Closed loop basically means the loop is closed using the feedback unit. At the load, so as to get the desired load performance, the sensor unit gets feedback on voltage and current also to operate the motor within the safe operating conditions. Because of our above advantages in several applications like diesel, locomotive shapes, the mechanical energy already available from a non-technical electrical prime mover is first converted into electrical energy by a generator. Then an electric drive is used as explained above. Okay, electric motors. Electrical motors. Most commonly used motors are DC motors. Now the DC motors are the type of shunt, series, compound. Shunt is basically parallel, if you are aware with that word also. Parallel, series, parallel and series together. So these things. So DC motors, we have types. AC motors, we have types, squirrel gauge, slip ring, all these type of induction motors. Special motors like BLDC, remember brushless DC motors. Here we have as a special case. So special motor like BLDC, step-up motors. DC motors have a number of disadvantages. Now let's see. Edison is losing right now in this paragraph. So DC motors has a number of disadvantages compared to induction motors. Edison motors are losing as compared to Tesla motors due to the presence of commutator and brushes. If you're not aware of this, you can look up to a induction motor diagram and understand the benefit of these two things. Squirrel cage motors are less costly than DC motors of the same rating. So my boy Tesla is providing us a more economical motor of the same rating, highly rugged, better in industrial use case, and simple. In the earlier days, because of easy speed control, DC motors were used in certain applications. Okay, DC is easier to use. But within the development of power electronics that supported Tesla, we now get the advantages of Tesla motors. Tesla was a future guy, present in the past, born in the past. AC motors, AC drives has become more popular. Yes, concept of multi-quadrant operation. Now, you must be scratching your head. What is multi-quadrating? We will look, we'll just see. What is multi-quadrating? What is this? What does it mean to have x-axis and y-axis replaced by speed, torque, and all these things? Okay, let me just take a water break, then we'll come back to this concept. And here we have also the same thing. Hmm. Okay, it gets deep into the review of DC motors, and I've forgotten my notes. So here we have the characteristics, the components, the sensing unit, source, modulator, technical terms, all these things. Quadrant of operation, here, dynamics, steady state stability. After this, we have friction torque components, load types, power proportional to, okay, dynamic of load mode, ठीक है, okay, dynamic of motor load system, dynamic of motor load, law नहीं, load, it should be load here. What do we have here then? Okay, this is also important. Steady state equivalent of a DC motor armature, flux, all these things. Shunt, separately cited, okay, speed torque, DC motor speed control. Okay, okay. I think this is in the notes after this, after some expressions. Okay, we'll first go through, according to our notes, the concept of multi-quadrant, and then we have dynamics of motor load. So we'll go through this only. Okay, try to get the length of this diagram. Till then, let me have a water break, guys. Oh. Okay, I'm back. Uh, multi quadrant operation. For consideration of multi-quadrant operation of drive, it is useful to establish suitable conventions about the signs of torque and speed. A motor operates in two modes, motoring and braking. So let's understand the first mode, motoring and braking. What is motoring and what is braking? In motoring, it converts electrical energy into mechanical energy which supports its motion. In braking, it works as a generator, converting mechanical energy into electrical energy and thus opposes the motion. Now consider equilibrium point B, which is obtained when the same motor drives another load as shown in the figure. Which figure? This figure only? A decrease in speed causes the load torque to become greater than the motor torque. Electric drive decelerates and operating points move away from point B. Similarly, when point working at point B, where is point B? Similarly, when point working at point B, an increase in speed will make motor torque greater than load torque, which will move the operating point away from B. Similarly, operation 3 and 4 identified as reverse motoring and reverse braking since speed in these is negative. Yeah, direction of motor and load torque and direction of speed are marked by arrows. Let's understand this. Direction of motor and load torques. Direction of motor, direction of motor, direction of motor, direction of motor. Okay. Load, load, and load. Okay, okay. Forward direction of motor speed will be one which gives upward motion. Okay, don't. What was written in the syllabus? Was it electromechanical transients? Yes, there is. Quadrants of operation. Machine characteristics are specified into speed torque and torque speed. Okay. Machine characteristics are speed torque and load characteristics are in torque speed plane. X to Y plane, Y is equals to Fx. Hmm. Okay, let's just try to understand this, not getting into my head. What are these things? Hmm. Let's see this load, torque, speed characteristics. And here we have learned that load characteristics are torque speed. So this is that, and where is so load, torque, speed characteristics. Speed torque characteristics of the load must be known to calculate the acceleration time and to select the proper time of motor to suit the load. So we have to find out the type of motor we need to use according to load. So what we will calculate? We will calculate the acceleration and speed torque characteristics. And for the acceleration, we need speed torque. And if we got acceleration time, we will know what type of motor we can use. The load speed torque characteristics of industrial loads are generally non-analytical function. Torque is function of speed However, some of them may be approximated to an electrical form such as constant torque speed, constant torque characteristics. EL gives to K. Most of working machines that have mechanical nature of work like shaping, cutting, grinding, shearing require constant torque, irrespective of speed. Similarly, cranes during the hoisting and conveyor handling the weight requires constant weight of material per unit. Okay. Then we have torque proportional to speed. Torque proportional to speed. So T is equals to constant omega, K omega. Separately excited DC generators connected to constant resistance load. Eddy current brakes have speed torque characteristics. A or B. So figure is of constant and this is for proportional. Torque proportional to square of speed. The third one is torque proportional to square of speed. Another type of load met in practice in the one is the one in which load torque is proportional to the square of speed, that is fans, rotary pumps, compressor. Torque inversely proportional to speed 1 upon omega. This should be certain types of lathes, boring machines, milling machines, steel mill, electric traction load requires this characteristic. So this is K omega square 1 upon omega. Okay, we got these. Let's check in the notes what we have here. Why it's not in this one? Do we have in this one armature voltage? Yeah, we do have it. Okay, let's read this. Go through this. Then what is this? Cosmic characteristic of semiconductor converter connected to DC. Okay, some numerics. DC series motor. Some numericals. Yes. Quadrant operation of chopper. Okay. Then question on motor. Okay. What is this control of induction motor? Huh. We'll start from this only. And also explain this. Hello. So now let's have a deep understanding on this thing first. You know, these part. The review of DC motor drives. So DC drives are widely used in application requiring adjustable speed, good regulation, frequent starting, frequent braking, reversing. Although since late 60s, it is being predicted that AC drives would replace DC drives. Even today, the variable speed application are dominated by DC drives because of a lower cost, reliability, and simple control. DC motors and their performance. Basic schematic diagrams of DC separately excited, shunt that is parallel, and series are here. So separately excited means the field winding and the armature are separate. Here we have aperture, here we have field. Both have different sources. Okay, shunt is basically both are in parallel, and series both are in series. In a separately connected to separate voltage, connected to the same voltage cannot be controlled independently. In the series, and the field flux is dependent on armature current. The steady state equivalent circle of a DC motor armature is shown in the figure. E is equals to K phi omega. Steady state. Resistance RA and the resistance of the armature. For separately excited and shunt motors, it is resistance of armature winding, and for series motors, it is the sum of armature and field. Okay. The output of characteristic torque speed characteristics, they can be obtained from motors, induced voltage and torque equations, plus the Kirchhoff voltage law KVL around the armature current. Okay. See, the internal voltage generated by a DC motor is EB constant A phi omega. It is also called back EMF, EB, back EMF. Okay. The internal torque T is equals to Ka phi Ia. KVL around the armature circuit. KVL EA is equals to EB plus IARA, where phi is flux per pole, that is in Webers. IA is armature current, amperes. EA is internal terminal voltage. RA is armature resistance. Omega is speed. EV is back EMF. T is torque. K is uh, motor back EMF torque constant. Okay, and it has volt second per radian length, Webers, or source. Okay, from the equation above three questions, we get the basic general relation between torque and speed. Remember this, guys. This is very important. We got the back EMF K into phi omega, torque K into phi current, and EA is equals to back EMF plus IR. So now we have to get the torque and speed relation. So torque was T and speed was omega. So let's see what we have, what has been done here. Omega is equals to EA upon K into phi. Omega is equals to EA upon KA upon phi. So phi and phi has been equated or what? No. Hmm. So KA phi will divide back EMF and by back EMF is EA minus IARA and EA minus IARA and IA is here, so RA. Oh, got the essence. So what it has done is omega is equals to EB upon KA phi. Back EMF upon constant into flux. And EB is EA minus IARA. So now EA upon KA phi minus IARA upon KA phi. And torque was Ka phi into current constant. So here we can see Ka phi into current is we are getting, but here this is in denominator and this is in numerator. So what we'll do is we'll multiply and divide. So basically in the numerator and the denominator. So RA Ka phi and Ka phi that will be squared. So here and Ka phi into Ia will become torque. So omega is equals to EA upon Ka phi minus torque Ra upon Ka phi square. So here is the relation. Shunt and separately excited motors. In their case, with a constant field current and field flux can be assumed to be constant. Then Ka phi would be another constant. Then the above torque relation would become EA upon constant minus Ra torque constant square. Yes, Ra is torque constant square. The speed torque of a DC separately or rated terminal full can be dropping straight line. Okay. The no load speed is given by applied armature terminal voltage. Series motor. In series motor, the flux phi is dependent on the armature Ia. Can be assumed to be proportional. So K phi is equals to Kf Ia. Now, phi for series phi is equals to Kf Ia. Something new. So torque is equals to Ka phi into current. Yes, it was. So now it will become for from this it will become Ka Kf Ia square because Ia will be there into denominator, so will multiply again. So phi Ia upon Ia square is equals to Kf. So what we have replaced is phi. So Kf into Ia into Ia. So Kf into Ia square and omega is E upon Ka phi. So phi becomes this only minus R A and F Ka Kf. So torque becomes Ka Kf Ia square and speed becomes Ea upon Ka Kf Ia minus Raf upon Ka Kf. Ia and Ia cancels out. Okay, got it. Ia and answer Ia and Ia will cancel out. So now what is this? E upon root KAF torque minus KAF. We have KAF here, KAF here, and torque is KAF I square. So we need one more I square. Okay, okay. KA into KF becomes KAF. It should be RAF upon KAF. So now speed becomes KAF IA. So KAF I square. So we have to multiply here I square. So it will be KAF IA square. So it will become torque. So torque and wait a minute. How does it got KAF torque? KAF is already there. You have to multiply by IA above and IA down, so it will become. I don't know how does it got it here. How it's speed? Okay, let's just see. Is there any explanation? No, there is no explanation. So what happened here? This part is understandable. Where did this root came from? Root should be KAF square and torque square. Oh, wait a minute. It can also be, if we put the value of, so KAF into AF into I square. So it will become KAF IA. So KAF IA. Then why are we taking root? Just to get torque hint. Oh, yes, we need the torque speed equations now. So torque upon IA is this value. Okay, so it will become EA upon IA upon torque. So I can say EAIA upon torque minus RAF KAF. Yeah, that is much simpler. Why can't we include IA? In the previous equation, we have included IA or not? Oh, there was no IA. So how to get rid of this IA? Now IA is torque upon KA KF root under. So IA becomes EA root under torque and root under KA KF. And root under torque and torque will cancel out to get root under torque. So it will become EA upon root under KAF torque minus RA upon KAF. Got it, guys, got it. So what we have to do is we don't want IA in this equation. So we have to replace IA. So if replacing IA, it will become torque upon KAKF under root the whole thing. So under root T upon under root KAF. So under root T upon under root KAF. So it will cancel out under root KF upon KAF. So it will become this will become under root KF, and here we have under root torque in the denominator. So under root KF into under root torque will become under root KF torque. So got it. So this is the rated speed of DC, and in this separately excited we have dropping line. Here we have this. So it is suitable for applications where we require high starting torque. Okay, and heavy overload. Since torque is proportional to square of armature current for given increase in the load, the increase in armature current is less than the series. Okay. According to the equation, as the speed varies inversely to the square root of the load torque, the motor runs at large speed at light load. Generally, electrical machines' mechanical strength permits their operation. Now, how can we control DC motor? We have two things, two methods. Guys, everyone is focus. I need here armature and flux. So remember the schematic diagram. We have armature, A and F field and armature. So in series, we have both of these together. So DC motor speed control, we have armature control and flux control. IA, RA, these are all armature parameters, and flux is phi. Torque speed curves at both separately excited motors and series motor using these methods are shown. Got it or not? Here in the separately excited, it was a dropping line, kind of dropping line. So the natural will voltage, we have the rated voltage VR, then V1, V2. So V1 is greater than V2, and these both are less than VR. But in series, according to the diagram, according to this, the speed torque will be like this. Here the speed will be constant with increasing torque. Okay, here it will be squared, inversely proportional. So V2, then V1, and VR. Torque speed curves with FC. What do you mean with FC? Flux control. So this was armature voltage control. If you control the voltage, given voltage, input voltage. And here we have flux. So just the opposite. If the phi R, then phi 1, then speed will be greater than phi 1. Phi r, then phi 1 and phi 2 will be the greatest. Here, phi r will be least, phi 1 and phi 2. Next, important features.